A quick little run through on the model that we developed mathematically to try to explain chemical kinetics. There are some observations that you would probably be fairly familiar with. In fact, even middle school students probably would be somewhat familiar with the idea that concentration of a reactant being increased typically makes the reaction go faster. Temperature also tends to increase rates of reaction. It does so drastically, actually. The effect appears to be exponential. I bring that up because if that's true, then any model that we propose to try to describe chemical kinetics should be able to account for the fact that concentration will have an effect to increase rate, and that temperature will also affect that and would affect it exponentially. So the model that we've come up with to try to explain chemical kinetics and rates at which things occur is typically known as the collision model, essentially that stuff has to collide to react. And we got to deal with an issue right off the bat that relates to some of this, and that is, if you believe a collision model is what accounts for chemicals being able to react, that they hit, that they have to come into contact, and if these two things are going to react, that somehow until they come into contact, there's no way for them to react. Then, let me just kind of adjust this here. Then, until you get to that point, you haven't accepted that that's the model that's appropriate. But I think most people would agree that things that have never come into contact aren't going to react. But we have a problem. If you were to look at the collision frequency, particles in a box bouncing around, the collision frequency can be known, can be calculated, and it turns out that the collision frequency is far greater than the reaction rate. And if you think about that for a moment, I hope that leads you to a logical conclusion. Not every collision results in a reaction. So it's like, how do we deal with that issue? Well, as it turns out, we have a Swedish fellow by the name of Arrhenius. He was also very noted for the theory of ionization of acids and bases that explain their behavior in light of producing hydronium ions and hydroxide ions in water. He believed the acids would give the H plus and the bases would actually give an OH minus, which is generally the definition we teach students first. And while it's a very good one, it's not quite as inclusive as it could be. Nevertheless, he's also noted for coming up with this concept of why doesn't every collision result in a reaction. And he basically postulated that there was a minimum activation energy. In the case of an exothermic reaction, where the reactants are higher in energy than the products, so we would have an enthalpy change. And it's worth noting that this enthalpy change is a thermodynamic quantity that is not at all dependent on what happens in the middle here. It just depends on the beginning and the ending states. It's a state function. So kinetics and rates is not driven by delta H, as we've seen, nor is it driven by delta S. Seems to be another factor. He proposed that in order for things to get from the reactant into the rearranged bonds in the products, that there was a little excited state, a little hump of energy here that had to be overcome before we could move on and form new products. In the case of an exothermic reaction, it would be maybe a little smaller, and then we would get that big drop of energy. But this part right here, labeled E sub A, which is energy of activation, that's the way it's labeled, this little bit is the bit that's got to be there. So if two molecules, for example, were to hit and they would not have sufficient energy to get them to the top of this hump, then there's no chance of them going on to produce products. And so in any sample, you have a variation in the kinetic energies of the particles, and not every collision is going to necessarily have the energy needed to get to that point. In the endothermic case, it's really not a whole lot different, but you will notice the activation energy
Daniels, call the office, please.
is considerably larger because we got to go all the way from low energy reactants up to this highest point and then make products. And typically that would make sense. Something that's endothermic doesn't tend to be as spontaneous, requires input, and has got a higher activation energy. It must be overcome to get it going. At the top here, whether you want to look at the endothermic graph or the exothermic graph, there's a spot right here that's an energy level here on the y-axis that you got to get to on these energy graphs. There are a couple synonyms for that. It's either called the transition state or the activated complex. If you could just try to picture what would happen when two molecules collide and they're going to try to make something new, some bonds have to be so they have to be weakened or broken. We got to be in a position for new bonds to form, and so basically, it's an energetically excited state that we don't really always know what it looks like, but it definitely is some slightly excited state where we're quasi between reactants and products, so to speak. It's not really the reactants, and it hasn't really formed the bond yet for the products, but it has been excited enough to be in a position to move forward with that. And so that was his explanation of why not all collisions have sufficient energy. You've got to get to a certain state before you can move on, this transition state, or activated complex, as it's sometimes called. And so he began to get the idea that perhaps he could estimate the number of collisions that would actually hit that activation energy threshold. And he said, look, okay, it's obviously a fraction of the total collisions, and there's a base E here, exponential number, with the exponent on the E of negative of the activation energy over RT. You'll notice that activation energy, if it were a larger value, is going to affect this power right here. Temperature, if it's a larger value, is going to affect it. To increase the number actually of things that would make that total collision threshold or have the threshold to hit the activation energy. The R value that we got to use is the 8.314 version, the metric version of the ideal gas law constant in joules per mole Kelvin. And of course, it probably goes without saying that any thermodynamic calculation of any kind or gas calculation is going to have the temperature in kelvins. So we have this exponential function here that Arrhenius postulated would actually give us an idea of what fraction of all the total collisions will actually have the needed activation energy. So let's look at issue 2 real quick that we got to deal with in this. We find that even when you take that into account, like if you look at those that have the required energy, they meet that threshold, the observed rate still falls far short of anything that would reflect that number. So the other question then becomes, well, if it isn't the energy of the collision that is the sole determining factor, what is the other factor? We come to believe here that it's the orientation. For example, perhaps if these two things hit like this, or perhaps they hit with a glancing blow that's somewhat ineffective. But if they don't hit with the right orientation is what this one gets at. Maybe they need to come in very specifically in a very specific orientation of collision in order for it to work. So we need to kind of add something here. And so we're going to add a factor that takes all this into account. Z in this, in ZP, reflects the collision frequency. This has given us an idea of how many collisions are actually occurring in there. P here is what's called the steric factor. If you've ever tried to work on something where you have to get both your hands in there and there just isn't room, you have been sterically hindered. In the case of molecules, their shape and orientation and bond angles and so forth can affect even whether they're a cis or a trans isomer, can affect how much stuff is sticking out in the road and interfering with, like, for example, access to a double bond, maybe a pi bond there that would normally be very reactive, but there is so many side groups and so things around it that nothing can hit it cleanly to get in there to commence reaction. So the steric factor it deals with shape and the probability that we're going to get a collision orientation that's going to allow the two things to actually react. So what we need to do is basically then pull all of this together if we can and try to deal with all of this at once. So if I could bring this to your attention here for a second. The rate constant, which has been a big topic of our discussion, K, apparently then might have several factors involved within that. The E to the negative EA over RT would be your energy term, and how many of them are likely out of the collision frequency we have, how many of them are likely to be of sufficient energy, and the P here, how many of them are likely to have proper orientation. Now I want to make a slight change to the equation to actually get to the Arrhenius equation. A here we're going to use as a replacement for ZP so that we can actually just have one term to deal with here for collision frequency and steric factor. And so if I rewrite this in a little bit more familiar order, the rate constant K would be equal to the frequency factor, which includes ZP, multiplied by base E to the power of negative EA over RT, where this is the activation energy of the reaction. So we have all those terms, and they do something a little bit unique to this that makes it come out kind of interesting. What happens if I were to take the natural log of both sides of this equation? I would obviously do that. I mean, I can certainly square or square root or do whatever I want to both sides of an equation. And so what ensues if you do that? Well, let me show you here real quick what ensues. If I take the natural log of K, I get the log of K. Now, I want to show you here, I had an arrow to show something here. I want to lay that right there. The frequency factor A is multiplied by this, so that can be a sum of two logs. And so the natural log of A comes from our frequency factor. When I take the natural log of this base E term, of course I eliminate the base E and take its exponent. And so separating out the term just a bit, I get negative EA over R multiplied by 1 over T. Now I have a very good reason why I separated that term out. If you look at this, this is very clearly a y equals mx plus a y-intercept here plus b type equation. It's linear in its form. So that means that we would be capable perhaps of analyzing it through some fairly simple means. And in fact, we can get the activation energy because it's related to the slope. If you look at what various k values, graphed versus 1 over t. Now why that? Well, log of k, here is my y term. 1 over t is apparently my x. And this would be the slope. So I could do various k's at different temperatures. And in fact, the graphs often look like this and are quite linear, which really backs up the idea that we have correctly modeled the behavior. The slope of the graph would be negative EA over R. And quite simply then, having a few k values and some temperatures and modifying those data so that we have the natural logs and the reciprocals and graphing that, we can actually get the activation energy because R is a constant. A couple things real quick as we wrap this up. There is a simpler form of this that I'll show you in just a second that's convenient for common everyday use. But you will notice that this model did include exponential dependence of temperature, did include most of the factors that we thought should have been there, and in fact seems to be a very good model. The one other thing here that I'll show you real quick is if you only have 2 k values and 2 temperatures, then the change in the natural log and the change in the x can be used to calculate slope. Well, this is a simple little formula with two k's and two t's. You can just plug those in and you don't need multiple.